Hey guys, welcome to another video on the course of network security. In this lecture, I will talk about key management and certification. Here is a brief roadmap for today's lecture. At the beginning, we are going to learn about symmetric key distribution using symmetric encryption. And then we will see symmetric key distribution by using asymmetric encryption. And finally, how we can actually distribute the public keys to the intended parties, the sender and the receiver. And we have a topic for assignment that is PKI, which stands for Public Key Infrastructure. So let us start with the first topic for today's presentation, and that is symmetric key distribution using symmetric encryption. As we know that for symmetric encryption, two parties must share the same key. That is the only secret. But the key must be protected. Symmetric key mean using the same key for encryption as well as for decryption. Okay, so if A and B want to communicate with one another by using symmetric encryption, they must have to share a common key, and that is the symmetric key. Why it is called symmetric key? Because the same key is used for encryption as well as for decryption. And as it is the only secret, so we need to keep this key protected or secure. Now, key distribution technique or mechanism actually refers to the mean of delivering a key to the two parties who wish to exchange data, but without allowing others to see the key. Mean we have a problem. The problem is that A and B want to share the secret, to share the key, and for that they need a mechanism how they would be able to agree on a common secret. Okay, for that purpose we have a solution, and the solution is key distribution techniques or key distribution schemes. Now for two parties, let's suppose the communicating parties are A and B. This key distribution can be achieved in a number of different ways. Some of them are here. Method number one. Communicating party A can select a key and then physically deliver this key to the communicating party B. That is the first method. You have to physically deliver the key, which is the secret, towards the B. Solution number two. Instead of delivering directly the key towards B, why not to assign the responsibility to a third party? So according to point number two, a third party can select the key, and then the third party will be responsible for the physical delivery of the key to both the communicating parties A and B. So the difference is that in one, actually one of the communicating parties select the key, while in two, a third party select the key and then physically deliver it towards A and B. That is the main difference between these two. The third technique is a bit different, and it says that if A and B, the two communicating parties, have previously and recently used a key, then one party can transmit the new key to the second party, encrypted by using the old key. Like if you have previously talked with the second party, and for that communication you have used a key, then you can encrypt the new key by using the old key, but this is dangerous, as we will see in a moment. And the last technique is that if A and B have a secure communication channel with the third party, for example C, then C can relay the key between A and B. Again, we are talking about the third party, and the third party has a major role in key distribution, as we will see in the coming slides. Okay, now if you give some attention, so the option 1 and 2, they actually need manual delivery of a key. We use the word physically, which means you have to deliver the key physically, manually to the other party. While in option number 3, as I just told you, that it is a dangerous mechanism. For example, if an attacker ever succeeded in gaining access to one of the key, then all subsequent keys will be revealed, will be disclosed. And finally, option number 4, we actually need a key distribution center, and the key distribution center will be responsible for distributing the keys to the communicating parties. But this is more secure approach. Each user in this case must share a unique key with the key distribution center. For the purpose of key distribution, mean you want to send the key towards B, but you want to make use of the key distribution center, then for that purpose you need another key that must be secure between you and the key distribution center, and we will see it in a moment. Okay, the use of the key distribution center is based on the use of a hierarchy of keys, and at a minimum level, two different kind of keys are required. Mean for each user there is a unique master key as well as there is a session key. The master key is shared with the key distribution center, while the session key, which is also known as temporary key, that has to be used between the two communicating parties. And the session key is used only for the duration of a logical connection, and after that session key must be discarded in order to be secure. Okay, session keys are actually transmitted in a secure way. You can say in encrypted form. And for encryption, we need another key, and that key is the master key. So master key, in summary, actually is a long-term key. And the master key is used for encryption of the session keys. And it is shared by the user and by the key distribution center. While on the other side, the session keys, they are temporary keys. They are used for encryption of data between the users for one logical session, and that session key is discarded after the use. And this is something about which disclose the information about the number of keys that is used. So in any case, the total number of session keys are equal to n into n minus 1 by 2, which means, for example, if n is equal to 3, then the total number of session keys are going to be 3 into 3 minus 1 is 2 divided by 2. It will give you 6 by 2, and then that is equal to 3. So it means that if we have a total of 3 communicating parties, then total number of session keys required are 3. While on the other hand, of uh, total number of master key is equal to n, which means 3. Now for example, if n is equal to 4, then in this case total number of session keys are going to be 4 into 4 minus 1 is 3, and divided by 2, 12 divided by 2, you will get 6. So in this case, if total number of communicating parties are 4, then total number of session keys are going to be 6, while total number of master keys are going to be 4. Why? Because everybody need a master key with the KDC. So we have 4 parties, we need 4 master keys, while everybody need a unique session key to communicate with the other party. So in that case, we would need a total of 6 session keys. Now let us consider a simple key distribution scenario. As we talk about key distribution schemes, let us see how it actually works. Now remember, the main topic is how we can use symmetric encryption for symmetric key distribution. Symmetric means one key So both for encryption and decryption, we are using the same key, and we need to securely deliver this key to two communicating parties. We talk about K distribution center represented by KDC, and we have two communicating parties A and B. Actually, A wants to communicate with B, but they need a public key, symmetric key encryption, and a public key. For public key, they have to take help of a third party, and that third party is KDC. Now suppose that each user shares a unique master key with the KDC. As we just saw, a master key has to be shared between the KDC and the user. So A has a master key with KDC and B has a master key with KDC. Also assume that user A wish to establish a logical connection with user B, and they require a one-time session key. Remember the session key? It is actually used, or it is actually shared between the two communicating parties. So in this case, the communicating parties are A and B. So each of them will need a master key to be shared with the KDC, and they also need a session key for communicating with one another. Now A has a master key, and that key is represented by capital K and A. This K A actually mean the key of A, the master key of A. Similarly, the master key of B has been represented by KB. These symbols need to be understood. KA is actually the master key of sender, for example A, and KB is the master key of the receiver, for example B. Okay, KB is the receiver master key, KA is the sender master key. For successful communication, the following steps need to occur. Step number 1. Here is step number 1. A actually issues a request to the KDC for a session key. Why? Because A need to protect the logical connection to B. So A will make a request to the KDC. The message includes, you can see, the identity of A, which is the sender, identity of B, which is the receiver, and N1, it is a unique identifier. Actually, in the language of security, N is known as nonce, Nonce. It could be any unique number, like a timestamp, like a counter, like a random number, and so on. So actually the request contains the ID of A, the ID of B, and this unique identifier, which is used for security purpose. Once the KDC receives this request, the KDC will respond with a message, and that message is encrypted. E stands for encryption. That message is encrypted. Okay, so again we have an encrypted message that is mentioned here. So we have actually two encrypted messages. One message is for A and the second message is for B. KA is the master key of A, KB is the master key of B. Okay, so the KDC respond with a message, and that is encrypted with K of A. Why? Because after this, only A will be able to successfully read the message. Why? Because it is encrypted with the secret of A. Only A knows the master key K of A. Nobody else knows. So who would be able to decrypt this message? Only the person or the body or the application who actually knows the KA, and that is the communicating party A. What is inside this message? Inside this message we have KS. Now KS stand for the session key, and this session key must be known to A and B, because there is the common secret. If they want to communicate with one another, they have to encrypt the messages with the help of this secret key. The same key will be used for encryption as well as for decryption. Beside from this key, you can see we have the identity of A, identity of B, and the response to the nonce or response to the unique identifier. And all these things are in encrypted form, and it is encrypted with the secret or the shared key of A. Okay, so this is important. Beside from this, we also have another encrypted message, and that message is encrypted with the secret key of B, with the master key of B, which means only B would be able to decrypt this message. Although this message would be received by A, but A would not be able to decrypt it because it has been encrypted by using the master key of B. What else we have inside this message? We have the same uh, secret or session key KS will be delivered to A as well as to B, and also the identity of A, because B would prefer to know who actually wants to communicate with him or her. So the ID of A mean the ID of the sender is also in the message. So in step number 2, the KDC responds with the message that is encrypted with KA, because only A would be able to decrypt the message or read the message. And it contains a one-time session key that is going to be used for the session, the original request message, which has the ID of A and the ID of B and a unique identifier. In addition, this response also have um, another encrypted message, and that is intended for B. It has two information, a one-time session key represented by KS, and also the identifier of A. It could be the unique address of A, for example, IP address or things like that. Okay. At step number 3, actually after receiving this response from the KDC, A will forward part of this message towards B. Now A will actually store the session key because it is going to be used for communication in the upcoming session, and then will forward to B the information that was originated at KDC for B, and that is like the session key and the ID of A. Using this session key KS, using this session key at the receiver side, B will generate another message at shown at it is depicted in step number 4. You can see E stand for encryption, is the secret key, and N2 is another nonce for security, is another unique identifier. To verify that actually the message was from A, is like a security challenge you are sending toward the sender. Hey, prove that you are A. It's like a challenge. So by using the session key for encryption, B send a nonce which is represented by N2 towards A. Now in step number 5, as A and B now have the secret session key that is represented by KS, A will respond to the challenge with F and 2. Is like the response to the challenge that was asked by the receiver, and F is a function that performs some transformation on N2. Okay, now if you give attention to this figure, you will notice that the key distribution involves in step 1, step 2 and step 3. All these things are only for the distribution of the keys, but step 4 and 5 and also step 3, they perform authentication functions. With the help of these n's, we are actually trying to prove the identities of the communicating parties. So this is how we can distribute symmetric key by using symmetric encryption. Before moving to the second important topic, it is important to understand that actually for large network it may not be practical to limit the key distribution function to the single KDC. Instead, we are going to use a hierarchy of KDCs. You can say there could be local KDCs which will be responsible for a small domain of the overall network, and for communication among entities within the same local domain. The local KDC is responsible for the key distribution. But if two entities are in different domains and they desire to share a key, then the corresponding local KDC can communicate through a global KDC. Mean the hierarchical concept is used here. Instead of using a single KDC, we are using multiple KDCs. Each one is responsible for a local domain. And this hierarchical concept can be extended to even 2 level or even 3 level or even more levels or layers. Actually, this hierarchical concept will minimize the effort that is involved in master key distribution, because most master keys are those which are shared with the local KDC, with its local entities. So if you are using multiple KDCs, you will get some advantage. Another advantage is that if one local KDC fail, it will not affect the whole network. Only that local area or local domain will be affected. Rest of the things will work fine. Now something about the lifetime of the session key. There are different arguments, there are different theories. For example, the more frequently session keys are exchanged, if you exchange the session keys more frequently, obviously the more secure they are, because the opponent has less ciphertext to work with for any given session key. On the other hand, the distribution of session key delays the start of any exchange, and it also places a burden on the network capacity. Okay, so on one side security enhanced, but on the other side actually the distribution of session keys place extra burden on the network capacity, which leads to delay. A security manager, a security person, security administrator must try to keep a balance between these considerations in determining the lifetime of a particular session key. There are some recommendations. For example, for connection oriented protocol, one choice is to use the same session key for the entire connection, for the entire session. Okay, by using the same session key, you can actually send and receive messages until the connection is open. Okay, now if a logical connection has very long lifetime, then it would be good to change the session key periodically. That is another recommendation. However, for connection-less protocol, there is no explicit connection initiated or terminated between the communicating party. There, the most secure approach is to use a new session key for each exchange of messages. So it depends. If you are using connection-oriented protocol, the recommendations are different. If you are using a connection-less protocol, the recommendations are different. Now let us move to the second topic, and now it is still we want to distribute a symmetric key, but now by using asymmetric encryption. And you are familiar with asymmetric encryption. They are also known as public encryption or public key cryptography. Here we actually uses a pair of keys, a public key and a private key for encryption and decryption. So if you want to share a symmetric key by using asymmetric encryption, we need to understand a simple secret key distribution scenario. Beside from its simplicity, this is still an attractive approach. Suppose A wish to communicate with B, then the following procedure is employed. A will generate a public-private key pair. PU here stand for public key, and later on we will see that PR actually stand for private key. Okay, so A generate a public private key pair, public key of A and private key of A, and then will transmit a message to B. This message will consist of two things: the public key of A and the identifier of A. In a similar way, B will generate a secret key. Actually, B will generate also a pair of keys, two keys, like the public key of B and private key of B. However, we are using this setup for the exchange of symmetric key. So if you think on this figure, you will see that A is actually not generating the symmetric key. A is actually sending a request towards B. Hey, here is my public key and here is my identifier. Could you please generate a key and then encrypt it by using this information? So B will generate a secret key, a common secret key, a symmetric key that is represented by KS. K stands for key, S stands for share. So B generated a secret key represented by KS, but this key is encrypted. E stands for encrypted with the help of public key of A. You see, it's very intelligent approach. A sent public key towards B, and then B is using that public key to send the secret key. Once this message arrived at A will compute, or in other words, A will decrypt this message by using the private key of A. So once A decrypt this message, A would be able to extract this secret key or recover this secret key represented by KS. Because only A can decrypt this message, only A and B will know the identity or the existence of this secret key. After that, A will discard the public key because there is no more need to use this public key and the private key as well. What they need for communication, they actually need this KS. So they will encrypt all the communication by using this secret key. Okay, this seems secure, but things are not secure. Okay, although A and B can now securely communicate by using the conventional encryption and the session key KS. Okay, as I just mentioned that they will discard the keys. So in this approach, no keys exist before the start of the communication between A and B, and none of the keys will exist after the completion of the communication between A and B. So risk of compromise of the keys is minimum. This simplest secret key distribution protocol seems secure, but it is insecure against an adversary. How? Let us see the insecurity of this protocol. Now we have the dirty guy, the hacker in place. A and B are replaced by Alice and Bob. We love them in our security world because they love to communicate with one another, but the problem is the dirty guy is always there and he or she try to capture the communication. Now if an adversary represented by D, for example, D stands for dirt. D has the control of intervening communication channel. Mean he or she is able to watch, keep eyes on the communication channel, or even look at the messages that are going to be exchanged between A and B. What will D do in this scenario? D can compromise the communication in the following way. How? Let us see. Steps are mentioned here. First, what will happen? Alice will generate a public private key pair. Remember? Public and private key pair. Okay? Along with identity of Alice. Okay, so public key of Alice along with identity of Alice has been sent towards B. This message is intended for B. It consists of the public key of A and the identity of A. But what happened? D can actually intercept the message, and after that D will create its own public private key pair, public key of D and private key of D, represented by PU of D and PR of D. PU for public key, PR for private key. So he or she generate a pair of public keys and then will transmit this thing towards Bob. You see, now Bob will receive public key and ID. But if you give attention, this public key is not Alice public key. It is dirt public key. But the identity is of Alice. So we actually change the contents of the message after intercepting the message. Now, after receiving this message, Bob will generate a pair of keys, public key and private key. Okay, so PUB stand for public key of Bob, PRB stand for public key, private key of Bob. Also, he will choose a secret key, KS. Remember from this slide, KS is generated by B, which in this case is Bob. And this is the secret that A and B is going to use for future communication. The symmetric key actually. Bob will send this message toward Alice, but we have a dirty guy in between. Again, D will intercept the message and will learn about this secret key. How? Because this secret key was encrypted by using the public key of the dirt. So dirt is able to decrypt this message by using his or her private key. So you can see D stand for decrypt. PRD, private key of D. Decrypt this message which was encrypted by using the public key of dirt. So he will apply the private key and will open the message and will get the secret key. And then he will change the message content again. Now he will send the secret key towards Alice and will change the public key of dirt by the public key of Alice. Now Alice would be able to decrypt this message as well, because this message has been encrypted with the public key of A. So it is able to decrypt this message with the help of the private key of the Alice. Now what will happen? As a result, both A and B know the secret, that is KS, and are unaware that the secret has also been revealed by this dirty guy, D. Now A and B can exchange messages by using this secret. Okay, B and the hacker, the dirty guy in between, will no longer actively interfere with the communication channel, but will simply eavesdrop the communication, and the communicating parties would not be able to disclose that things goes wrong. Okay, now as the dirty guy can have the secret, so he is able to decrypt the messages, and both A and B are unaware of the problem. So this approach is not a secure approach. We need something else, and for that we need to properly distribute the public keys. Okay, for that we have 4 different approaches, and these approaches are commonly used for distribution of public keys. Every approach has a merit and demerit. Let us briefly explain these approaches. The first approach is known as public key announcement. This is very simple approach. Any participant can send his or her public key to any other participant, or even he or she can broadcast the key to the community at a large. Just we can see A publicly announce the public key to everybody else, B publicly announce the public key to everybody else. A major weakness is that anyone can fork such a public announcement, as we just saw in this case. Okay, so there is a major weakness. Some user could pretend to be user A and send a public key to another participant or broadcast such a public key. So it is insecure. Second approach is, why not to have a publicly available directory of public keys. By using this approach, a greater degree of security can be achieved by maintaining a publicly available dynamic directory of public keys, more secure than the individual public announcement, as we just saw on the previous slide. However, maintenance and distribution of the public key directory would have to be responsibility of a trusted entity or organization, and such a scheme would have to address 2 elements. The first is that this authority maintain a directory, for example, which will contain records of each and every entity involved in the communication. The fields of the record could be like the name of the identity or the unique identifier and the public key of that identity. And the second requirement is that each participant will have to register a public key with that public key directory. For example, the public key of A is PUA and the public key of B is PUB. Both these parties will register these public keys with the public key directory, and for that registration they need to trust this third party. Beside from these two requirements, there is also another requirement, and that is that a participant may replace the existing key with a new one at any time, because maybe the previous key was too old, outdated, or maybe that was compromised. So there must be an option to update the key. And also another requirement could be that participant could also access the directory not only in person but electronically as well through internet. And for this purpose, secure authentication communication from the authority to the participant is mandatory. So these are some requirements for publicly available directory. Our third approach is more secure, more sophisticated one. By using this approach, stronger security for public key distribution can be achieved because it provides tight control over the distribution of the public keys. As we just saw in the previous two cases, the security was not that much tight. However, here in the public key authority, it is much more secure approach. And a typical scenario is illustrated in this figure. Actually, the scenario assumes that a central authority like public key authority will maintain a dynamic directory of public keys of all the participants. How it works, let us see. Suppose Alice wants to communicate with Bob. Alice is represented by A, Bob is represented by B, and the authority is represented by public key authority, or you can say a public key distribution authority. Well, first A will send a request to the public authority. This request will contain a T1, which is like a timestamp of the message. And the request is for a key that this A could use to communicate with B. Hey, I want to communicate with B. I need a key. Could you please provide me a key so that I can communicate with B? That is the request. And then the server, the public key authority, will respond in step number 2. The authority actually responds with a message, but that message is encrypted. E stands for encryption. The message is encrypted. How it is encrypted? That is encrypted by using the authority private key. PR stand for private key, auth stand for authority. Okay, so this message is encrypted with the private key of authority, and it could be decrypted only with the public key of the authority. Okay, that is what we know from cryptography. And what is inside this message? Here are the contents. The same message that was sent by the sender. You can see the request and T1 is sent back. And this is something new. Public key of B. You see, every body public key has been registered with this public key authority. A public key is here, B public key is here. A want to communicate with B, A needs the public key of B, so A will request this authority and the authority will send the public key of B towards A, but that public key, that message must be encrypted with the authority private key. That is what happened in step number 2. Now, A would be able to decrypt the message using the authority public key. Therefore, A is assured that the message or it is originated with the authority. No one else has been sent this message. The message is intact from the authority. because it will only be able to decrypt this message with the public key of the authority, and A has access to the public key. Okay, now inside this message we have the B public key, and this public key will be used by A for encryption of message destined toward B, and also the original message, the original request used to enable A. Actually, this message, why this message was resent toward A, because it will enable A to match this response with the corresponding earlier request to verify that the original request was not altered before reception by the authority. Maybe someone can change this request on the way. So to make sure, A has to recheck this original message. Now what happened in step number 3? A actually store B public key and also uses this key to encrypt a message. Okay, so here you can see a message is encrypted with the help of the public key of B. What is inside that message? Identity of A and a unique nonce, unique identifier. The message is sent toward B. Now B in step number 4 and step number 5, you can see now it's time for B to verify something. B will actually, as B receive the identity of A, B actually retrieves A public key from the authority in the same manner as A did. Okay, so 1, 2 are the steps that are similar to step number 4 and step number 5. Mean B also need the public key of A. So B will request the authority, hey, somebody want to communicate with me. Could you please provide his or her public key to me? And then the public key will be provided. And then after that, in step number 6, B will send a message towards A. Now this message is again encrypted. This time the message is encrypted by the public key of A. Now only A would be able to decrypt this message. What is inside this message? Response to the previous challenge and one and a new challenge. This is for authentication purposes. Okay, they want to make sure that actually A sent the message and A want to make sure that actually B sent the message. So now you see we do not have exchange any message. We are just requesting for keys, we are just requesting for authentication and things like that. Finally, it's at step number 7, A will return the challenge, response to the challenge and 2. Okay, but again this message is encrypted by using the public key of B, so only B would be able to decrypt this message. And finally after this A and B would be able to communicate with one another by using the secret, by using the public keys of one another. And this is how we can actually distribute the public keys to the intended communicating parties with the help of a public key authority. If you give attention to this figure, you will see that the initial 5 messages until here, they have been used for distribution of keys. And these 5 messages need to used only infrequently. Remember the drawback, if you use them for any session, every message, etc., then it is going to be increase the load and will lead to delay. So both A and B can save one other public keys for future use. For example, in future, if A want to communicate with B, then A will not request again for the public key of B, because A has already stored the public key with him or with her. Now the final method for key distribution is the use of public key certificates. I will not go into further details because you have already studied the public key certifications. So the basic concept is that instead of using the keys, why not to use certificate instead of using the keys or the messages. And as we know that in a public key authority, in the previous case, a user must appeal the authority for a public key for every other user that it wishes to contact. For B, these steps. If A want to communicate with C, same steps. If A want to communicate with D, same steps. Every time A wish to communicate with a new communicating party, A has to generate a request for the public key of that communicating party. An alternative approach is to use a certificate that can be used by the participants to exchange keys without contacting the third party or without contacting the public key authority. And we know the concept of certificate from the previous lecture. Typically, the third party is a certificate authority, like government agency, like financial institution, like third party broker, on which the customer can trust. A user can present his or her public key to the authority in a secure manner and obtain a certificate, just like this. Hey, certificate authority, this is my public key, could you please issue a certificate to me? Now, what is inside this certificate? Actually, if you open this certificate is encrypted by using the private key of the authority. It contains a timestamp, the identity of A, and this is important, the public key of A. Okay, so all these things are encrypted with the private key of the certifying authority, and only A would be able to decrypt this message. This is like a certificate CA. Okay, now if A want to communicate with B, A will present his certificate. The process is simple. If B want to communicate with A, B will present his certificate, and the certificate actually contain the public key. Okay, we need this public key for communication, and that public key is embedded inside the certificate, so they will present their certificate to one another. So this is how public certificate works. And finally, I would like to mention that there is another concept which is known as public key infrastructure, or PKI. It has an important role in the key distribution setup as well. So I would like you to dig some efforts, put some efforts to explore the concept in more details. So this was about today's lecture, and it was about distribution of keys. Thank you so much for attending the lecture. See you, take care, and goodbye.